Part 5. I gotta admit, not a lot of apples in Part 5, which is a shame. The Taylor series is not a shame. It connects powers and derivatives and factorials, which are weird. What are they doing there? Well, if you believe in the power rule, which is like differentiation 101, then we should be okay with it. Instead of trying to prove it, let's just see it work with Tiger's first equation. There it is, and yeah, it's got a bump. It's a handsome equation. Let us use the Taylor series on it, and you will see something pretty clever come out of this, I promise, even though it doesn't seem like much. It's just, well, what is it? It's a plus 0.3a squared minus 0.2a cubed. That's the 0th derivative, that's the function, at x is equal to a. And guess what? That's right, we will once again let a equal 0. Which again seems like we shouldn't be allowed to do that, but we are, and we have, and the first derivative is 1 plus what, that's the 2 times the 0.3 is the 0.6x, and x is equal to a. And again, it's 0.2 times 3, this time is, again, negative 0.6a squared, and again, we are letting a equals 0, so does it all go away? No, it does not all go away. We're left with an x, just a small little x, a brave x. The second derivative, 0.6 minus 1.2a, and again, we let a is equal to 0. I feel bad every time I do it, but there we have it. And do you see, it's clever, do you see with the third derivative, do you see what we're doing here? And we have an x cubed over 3 factorial. 3 factorial is 6, so 1/6. And do you see what it is? We have taken apart and reassembled the same function that we started with. Crazy. That's the neat thing about the Taylor series, is that, well, it works. And did you see how the factorial came into play there? Thanks to the power rule. So now that we've got that out of the way, let's do it for Owl's equation. Owl's equation is kind of neat. F of x is equal to x to the ex. I like it. It's kind of like y equals ex, but it's got a little bump in it. It's a handsome equation too, I feel. Let's get to work with the 0th derivative. And again, a is equal to 0. 0, 0, it's a 0, right? Yeah, okay, it's 0. And then the first derivative, we have x times the derivative of e to the x, and that's just e to the x, plus e to the x times the derivative of x, which is 1. Okay, I believe like this takes a little bit of looking at, but there's the first derivative. There's our 1 over n factorial times x minus a raised to the 1 power this time, because n is equal to 1 and a is equal to 0. And it tidies up nicely. We have x. The second derivative again with what's called the product rule. The product rule for differentiation here is kicking out these e to the a terms, and then they're going pretty much away as we let a equal 0. So there's the second term, and then we have the third derivative, or we have the third term with the second derivative, and with the third derivative we have the fourth term, again with a is equal to 0. When a is equal to 0, we have 3 over 3 factorial times x cubed. So we once again built a function, built a power series representation for a new function, x e to the x. It doesn't just work for e to the x, it works for x e to the x. Also, only does it really work? And you can express the series in a couple of different, does it work? Well, let's see, does it work for 0? And there it is, and 0, 0, 0, 0. Does it work for x is equal to 1? E to the 1, we know that. And our measly 3 terms here aren't too impressive, but if you run it out to 10 terms, you get a good value for e. So it works for x is equal to 0, works for x is equal to 1. Does it work if x equals 2? No, it doesn't, unless you go out to multiple terms. When I was trying this, I didn't think it was going to work, but then I tried it with a spreadsheet and I got it out to 10 different terms, and lo and behold, it matched. And if it works, I'll buy it, but if the car doesn't start, I'm not going to buy it anyway. We have here a way of writing out this function. What do we mean by writing out this function? Well, let us write a graph rather, for y is equal to 0. There's our graph for y is equal to 0. It's pretty flat. There's our graph for y is equal to 0 plus x. That's what that would look like. All right, so there's the first two terms. We're getting a better and a better approximation of this function. Next, we have a graph for y is equal to 0 plus x squared. You know what x squared looks like? This is 0 plus x squared. Getting better all the time. Now here is the graph for 0 plus x squared plus, what's that, 1/2 x cubed. It looks like that. And it looks pretty good, at least for positive x. Negative x needs a little bit of help. But I tell you that if you keep on doing this, you'll eventually get that. Even though the graph does sort of wag its tail back and forth. Hey, look at that. The graph wags its tail back and forth for a little while. But it does work. You create the same graph, and it works for all x's, even though it's only supposed to work. It was only promised to work for x values around x is equal to 0. Anyway, we can add this to our series of series. It's a series of series, or a group or a mess of series here. E to the x, check. Cosine x, sine x, we did those two, check. We did e to the gamma x, double check, for x, e to the x, and they all worked with the Taylor series, which is this. Should I even try to put that into words here? F of x is equal to the sum from n equals 0 to infinity of f to the nth derivative of a, the function at a, over n factorial times the quantity x minus a to the n power. And we always let a is equal to 0, and that made life easy and nice, and it always worked until now. Because now it stops working. Now it stops working for an equation that is in all the textbooks, on all the websites. Tiger's favorite equation, f of x is equal to 1 over 1 minus x, and there's the graph. And we've got problems. We've got an asymptote. That's going to be a problem. How do you express an asymptote in a power series? You don't, and here's why. Because this equation will not work, but let's try. Let's give it a good solid try, and let's skip over all the details. Thankfully, we're skipping over those. But if a is equal to 0, life gets clean. We're cleaned up pretty good. I mean, the function's not going to work. It's a clean car. It's not going to run, but it's clean. Anyway, let's take a look at it. Here's our graph again. Does it work at x is equal to 0? Yes. Looking at that, it does work at x is equal to 0. Both sides are 1. Does this equation work at x is equal to 1? No, absolutely not. It gives us an error. Dividing by 0 is still totally not allowed. Does it work at x is equal to 2? Also, definitely not. When somebody's looking at that equation and saying, what do you mean it doesn't work? Well, you look at the sum from n is equal to 0 to infinity of x to the n. That's what we're looking at there, and quite clearly that goes to infinity. So it doesn't work at x is equal to 1, does not work at x is equal to 2. What about x is equal to negative 2? It doesn't work there either. It doesn't work there. We know that 1 over 3 is equal to 1/3, but the other one, the x to the n, the negative 2 to the n power, that thing oscillates crazily. It oscillates from negative to positive. We had a snake function like that earlier. That's not allowed. That's not going to converge somehow to 1/3. It does work, however. This power series does work at the wonderful value of x is equal to 0.5. You have to use a couple extra terms to see it start to work there, but there it is at 0.5. It works. Good. Why? Well, for now, we'll just say that quantity 1 minus x to the negative 1 power is equal to the power series expansion 0 to infinity x to the n only for values of x between negative 1 and 1. Which means that for once the Taylor series was right. Or again, what did we do? We said that a is equal to 0, and then it only worked when x was near a, 0. Which gets confusing because you got three things. You got the 0, the a, and the x, and they're all different, but then sometimes they're all the same. Well, anyway, for this small range, this equation works. Let's draw it out here. Here's y is equal to 1. Looking good. Here's y is equal to 1 plus x. Also looking good. Y is equal to 1 plus x squared gets happy. And if you add in the next term, it gets like that. And it does seem to work well if you stay in that nice range. What about over here? What about it? A is equal to 3. Could we write an equation for a is equal to 3? We had a good run, Taylor, but your goose is cooked. No, Taylor still works. And see, this is what was confusing me for a long time here. I was talking about the Maclaurin series as being a special case of the Taylor series, but it's not really a special case. Anybody can let a equal 0. What's special about some of these functions that converge like they do, that like we just showed, what's special about those functions, not about letting a equal 0, what's special about those functions is we let a equal 0, and the Taylor series expansion, the Maclaurin series expansion, still worked for all x's. That's not guaranteed to happen. That didn't happen for 1 over 1 minus x. That didn't happen there. It's not guaranteed to happen. So instead of thinking of the Maclaurin series as a special case of the Taylor series, I'd like to think of some functions are Maclaurin-likable because they still work all the time for all different x's, even when a equals 0, but no one likes to say things like that. Taylor still works. That's the point, is that we will still have success here. We just have to let a equal 3, and we can do that. This is the last one of these guys, so take a deep breath and let's do it. There's the 0th derivative. There's the function. There's our 1 over n factorial term, and we are, like I said, going to let a equal 3 this time. We're going to let a equal 3, and then we can clean that up just a little bit. Here's the first derivative. Again, we're using, what are we using here? We're using the power rule. We're using the power rule and also kind of like the function rule there. That's why it's not negative, because we took the derivative of 1 minus x to all to the negative 1 power, and then we had the negative 1 from the power, and we also had the negative 1 from the x, the derivative there. Anyway, what happens if we evaluate this at a is equal to 3? That's what happens. And then it cleans up a little bit, and it cleans up a little bit more. All right, I only have the stomach to do one more of these, and I know I'm going fast. You can, no one's going to slow it down and check my work, and if you did, heaven knows what you'd find, but there's the second derivative and the 1 over 2 factorial term, and we put them in there, and then we let a equal 3, and then we clean it up and clean it up a little bit more and combine like terms, and that's all we're going to do, and that's enough, and that makes Owl happy, and that's our, because it's a new equation, so Owl gets to grab it because it's a new equation. It's not like our other series that went on forever, but only for certain values of x. This one goes on for values of x equals 3, so let's see if it works at x equals 3. Yes, it does. If x is equal to 3, this equation works fabulously. How about x is equal to 2? From earlier, x is equal to 2 blew up to infinity. Here it's pretty much okay, and I bet it would be okay-er still if we had more terms, but I'm not going to check it because I don't care that much. But one thing I did think was kind of pretty, at least, was drawing in those lines. So our first line is at negative 19/8, which is a little bit more than 2, I guess, a little bit less than 2.5. I drew it there. Anyway, how about that plus x? That'll give us that line, and then if you add in a negative 1/8 x squared term, you'll get that. And it looks like we're doing okay, approximating 1 over 1 minus x at a is equal to 3. Got it. So that guy belongs in the zoo. Put that series in our series of serious, or serious series of series. And Tiger and Owl will keep an eye on him and know that it only works between negative 1 and 1. Or you could write out a different power series expansion, but now what about apples? And cutting apples apart, and why do we have to keep our eye on that particular series? I'll tell you about apples. When you cut apples in half, it's a big job. And you got to cut it in half, and then in half again, and in half again, and in half again, and in half again. This is a new series. And then in half again, and so on. There's our new series. And clearly we all agree that this series gives us an apple. But why? Because it's getting smaller. Like this exponential decay type function. It's getting smaller, that's why. Or, to be more specific about it, more formal about it, because of the ratio test. You guys want to use the ratio test to check out some of our series? No? Well, we're going to do it anyway. And you can, again, look at the details, and so far so good for the apple cutting function, but we knew that would be the case. What about e to the x? Let's take a look at that. Same method, slightly different details. Yada, 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 yada. Hey, this is kind of neat. This is kind of like the battle between the factorials and the powers. The battle between the factorial, it looks like the Factorials win. Yeah, the limit as it goes to infinity, yeah. You can't let x go to infinity like you can for n, so no matter what value you have for x, x to the n is going to be less than n factorial as n goes to infinity. E is so cool. Anyway, here's cosine and sine. They were just part of E, I guess. And if that, going back to E, if that's true, then that's true for any gamma times x, because you can't let gamma times x be infinity as n gets to be infinity. No, wait a minute. No, stop right there. That's not right. Earlier you were saying that they had to get smaller and smaller and smaller. The pieces of the, like when you were cutting that apple, that they had to get smaller and smaller and smaller. But e to the x clearly goes to infinity, so you're nuts. Well, no, you're thinking of it the wrong way. So you're thinking of it the wrong way. You're thinking about what happens to the function when x goes to infinity. We're thinking about what happens to the slices when n goes to infinity. See the difference? Get it straight. That's why I don't teach math. We're getting close to the end here. But this is different. X times e to the x. This one's different, although it's also kind of the same if you work out the details on your own. This guy, however, clearly, if you look at x to the n, that guy only works if x is between -1 and 1. That's the only case in which the limit as n goes to infinity of a to the n plus 1 over a to the n will be less than 1, and we're done. Done? Which is unfortunate, because I'd hope you'd be able to add to this neat list of numbers. This neat list of numbers from the end of part 3. We had the fractions being invented, you said, or discovered by addition, and then we had the irrational numbers discovered, you said, somehow by multiplication, and then the imaginary numbers discovered somehow during rotation. How did that work? Tell me more about that stuff. All right, well, once again, the number line, and we're dancing around counting apples, and there they are. But what about all these missed fractional numbers? If you just have the integers, you are skipping over fractions, and that's a shame. But then even if you have every single fraction, every single number that can be expressed as a over b, you are still skipping over, we said, some irrational numbers. There's some more holes in your number line. And there are also ghostly numbers orbiting around, spooky numbers, imaginary numbers around the number line that you might be missing also, unless you get serious about exponentials. And that's all the numbers there are, except it's not, because there are other missing numbers. E and pi are transcendental numbers, and there they are, holes in the number line. And what do I mean by that? They are not integers, of course. They are not fractions, of course, and you cannot express them as a power series. Oh, isn't that exactly what you just said you could do? Earlier you said you could express E like this. Nope, you can't express it. You can get close to it. It approaches it as a limit, but you never get there, because if you got there, you'd stop. And if we're going to infinity, honey, we're not stopping. So anyway, you can't express it as, even if you could make up the craziest, they prove this. Even if you had the craziest power function with all these different powers and all these different logarithms and everything you could possibly have, they're not going to make E. They're not going to make pi. E and pi are, however, connected. Just like slides are connected with stretches, just like rotations are connected with derivatives, are connected with directions, are connected with math. Which, despite all that, is still a pretty good way to count your apples.